All right, well, welcome. This is my talk about Practice Makes Perfect Extreme Cassandra Optimization. I did not pick that title, but it is better than the one that I chose. I hope you'll get a lot. I'm going to cover a lot of technical information. I'm going to move fairly fast because there's a lot of content. A little bit about me. This is going to be short. I'm sure you guys are tired of hearing about all these different companies and how they're special and unique. I'll just say Uella is really awesome. We've learned an awful lot about how not to manage Cassandra clusters and how to do it correctly. I'm going to talk a lot about that. It's been a process over the last couple of years of just gradually making incremental changes and making things a lot better, or more colloquially, make it suck less. I'm introducing a term that I think is new that I think describes what a lot of us do in terms of performance and how you make Cassandra or any distributed system or even a single system perform better, and it's what I like to call being a heuristician, which is using heuristics rather than being more scientific, which is expensive and takes a long time. I'll talk about that more in a little bit. I'll talk about tools that I use that maybe you haven't seen before or didn't know how to use them correctly. And then at the end, if I have time, there's a lot of settings, like I'll go more into depth about specific settings that we use at Ooyala, and then I got a couple of little things about file system usage, how we're using BTRFS and ZFS to make our clusters store a lot more data, run a lot faster, and a lot more flexible. About me, I'm tech lead of the Compute and Data Services team at Ooyala. We're a DevOps team, and that means a lot of different things to a lot of different people, but what we do is kind of the more pure DevOps in that we do the entire stack, bottom to top, hardware, software, operating system, database tuning, all the way through. And what we're building is a platform for Ooyala to use Cassandra and Hadoop and all of these different large big data systems so that all the engineers don't have to get concerned with how do I set up Hadoop? How do I interact with Hadoop? So we're building services in front of these systems so that all the developers can't have to do is just know where the service is, submit their jobs, and then forget about it. We have about 100 Cassandra nodes spread across 8 to 10 clusters. This is probably going to more than double in the next month or so. And then obviously the obligatory, we're hiring, make HR happy. Ooyala was founded in 2007. Most of this stuff is pretty boring, 230 employees, 200 million unique users. The important one on here is 2 billion analytic events per day. All that data, all those analytic events have to be stored somewhere, they have to be processed somewhere, and we need to be able to serve the results of that data to our customers as fast as possible. And that's where Cassandra comes in. We've been with Cassandra since 0.4. It's been a rough ride. These days, it's a lot smoother than it used to be, thanks to DataStax and Akunu and other companies that are contributing to Cassandra a lot more than we are. We really appreciate all their efforts in stabilization and operational support. Use cases that we have, all of our analytical data, I have a slide on this in a minute, but basically gets batch processed and the results of all of our rollups and things get written into Cassandra so that those can be exported to our web interfaces for our customers to use. And Cassandra provides us that very low latency ability to fetch values and show them to our customers. We also use it in various places as just a highly available key store. Forget all of the columnar storage and all of that. It's a really nice distributed key value store so that you just don't have to think about cache coherency or, do I connect to Memcache D1 or Memcache D2? Do I deal with hashing? You just forget about all that crap. Connect to any node in the Cassandra cluster and your data's there. We have an internal monitoring tool called Haster that we use to track all of our metrics. So there's a statsd style interface. It's basically in place of where you normally use Graphite. That's currently receiving about 50,000 metrics a second, writing that into a Cassandra cluster of 5 nodes. We use it for playhead tracking. So if you've used Netflix and you're watching a movie on your iPad and you pause it and then you shut it down and then you go to your TV and you bring up the same movie, it'll resume where you left off. We use Cassandra for the same thing. I'm pretty sure Netflix uses it for that too. Then machine learning data. So we have a bunch of ML stuff that we run in Hadoop that generates outputs that we store in Cassandra so that we can use things like georeplication to get it out to the edge that's in EC2 and do cross data center movement. So this is our current analytical pipeline. This is kind of the more interesting bit. So what happens here is our players when you're watching a movie, say on ESPN.com, every few seconds we'll send a little update to us telling us where you are in the movie, if you're having buffering issues, what bit rate you're at, a bunch of different little things like that, your IP address so we can do geo-tracking, things like that. So all that data goes and it gets HTTP pushed to our edge, which we call the loggers. That data gets crammed into S3, which is a big black box on purpose because that's how we treat it. And then our Hadoop cluster pulls all that data down into our local HDFS for crunching, and then that writes into Cassandra, and then so on and so forth. And the Abe service is basically just a front end to Cassandra that our web tier can access to get to the data. So here's right, there's something I was going to talk about there. So that read modify write there, I don't have access to my notes, so there's a weird setup here. Read modify write is what I want to talk about first for performance. So if you can model your data for Cassandra in such a way that you can avoid doing read modify writes, and what that means is when you go and you fetch a data from the database, you maybe increment it or you add a number or you append a string, and then you write it back in the same location, the same row key, same column key. You're going to have all kinds of issues with consistency. It's harder to do distributed systems on top of it because now you have to do distributed coordination, which is going to get easier in 2.0 apparently. But also, like, avoiding that, just you can do a lot higher throughput, doing things like we do with our metric system, which is entirely insert only, and the read side is completely separate. So we can just jam in those 50,000 second. We don't even think about synchronization. We run 5 instances of the service, and we just don't have to worry about any kinds of performance issues there. There's no sharding, there's no consistent hashing at the service layer. It just writes into Cassandra, and it doesn't matter which one does the work. So kind of an example of what happens when you do read, modify, write. So I came up with this example. So I was trying to think of an example, and I thought, well, a good thing to model would be how much my team is going to drink. They're here. Almost my whole team is here. So I said that, we have Philip. He'll probably drink a lot. He's a beer guy. So he's got 12 drinks. We got Christoph. He's in London. Nobody in London drinks, right? Kelvin doesn't really drink a lot. Frank's a nice guy. He drinks a few drinks every now and then, and so on. So getting closer to the conference, a couple days later, the mem table has been flushed to disk into an SS table, and I want to make an update. So I go and I read the value out or maybe I just overwrite it, and I say, I update, like, I'm not going to drink that much because I have to talk on Wednesday, and Wednesday night I got to go home, so I'm not going to drink anything. And Philip tells me he's quit drinking. I berate him for his lack of dedication, and then update the column value. And then closer to the conference, I decide, wait, hold on, I'm going to be out drinking with all you people, so obviously I'm going to drink a ton. So I update my value, but instead of just updating it, I actually pull the value out, and I read the value out, and I add 20 to it, and then I write it back. So now that's sitting in a mem table in Cassandra. There's an SS table on disk that has the old value. So now you're back into conflict resolution territory. And there have been other talks about conflict resolution. I'm not going to go into that right now. But what this means is now you have to compact before you get totally consistent, right? You have 2 values in your database system until all of the compaction stuff fires. So by avoiding read, modify, write, you just don't even have that problem. Your compactions are going to be a lot smoother. You're going to have a lot less conflict resolution stuff to deal with. And that's kind of the lesson there. And then finally, after a while, it all gets compacted down, and that's what it looks like when it's all done. So if you have a lot of hot data, one of the patterns I really push our developers to use is to do that insert workload to the point where we actually do stuff where we waste work. So we'll actually insert the same value twice sometimes. Insert over the same key value, same set of keys, the same value, and let Cassandra's conflict resolution take care of all the overwrites. And it works really well for us. So moving on, so that's our old architecture. So here's a bit of the practice makes perfect stuff. So in 2011, when I started at Uella, we were running on Cassandra 0.6. All kinds of operational issues with it. But the most important one is that if you've been with Cassandra for a while and you kind of know how it works, it has this property of once you start up a cluster and get it kind of working for the most part, it's easy to forget about. So we had this 18-node Cassandra cluster sitting there for years, and people just forgot about it. People forgot to do backups. They forgot to do compactions because we were still on size tiered. they forgot to do repairs. And we have that heavy read, modify, write workload, and we had some deletes in there, so we had expired tombstones, we had all kinds of issues with the data. So what ended up happening is to get to 0.7 and 0.8, ended up being 0.8, we looked at all the different options for reading data out of Cassandra with their tools, and there wasn't a lot of good tooling there. And one of our guys said, well, I'll just rip the data out of the SS tables and in a big MapReduce job and write it back out to Cassandra. And really, you can do that? And it's, yeah, it'd be easy. Are you sure you know what that word means? and you know, he's one of these wicked smart guys. We have a bunch of them running around, and so he went and he wanted to play with Scala, so he used Scala. He pulled the SS table classes right out of the Cassandra source, wrote a MapReduce job that could read the SS tables and then write back into the front end of Cassandra. That way the clusters are completely separate. This is all happening in production, and we needed to do the whole migration with 0 downtime. So what we did is, it was like, well, if we could pull all the snapshots into HDFS and just process them there, that would be really nice. But we didn't have enough space in the Hadoop cluster and no time to buy more capacity. So I said, well, we'll just do this trick. We'll export over NFS all the snapshots to the Hadoop cluster and do this big crossover, everything mounts everything craziness. It turns out the kernel we were running at the time had been on there for years and didn't have NFS support, so well, crap. And so looking around, like GlusterFS point-to-point actually worked out great. So we did GlusterFS point-to-point export, the same mishmash mess, and ran a MapReduce job across it. Completely saturated the network for 3 days. And at the end of the day, we had a nice new cluster with completely consistent data. We'd scrubbed out all the expired tombstones, fixed up all the inconsistencies, and rebuilt all of our indexes. And that's our first migration. If we do this again. So lessons learned there. Don't forget about your Cassandra cluster. You know, doing those repairs regularly and things like that. If you keep on top of it, you're not going to have these kinds of issues and have to do these kind of nasty migrations. It turned out for 06, 07, we kind of had to do something like this anyway, but it's just a really interesting way to move data. I think if you look at Priam, it has some ways to actually do some similar kinds of things by ripping SS tables out of S3 and things like that. So while this transition is happening, I had the opportunity to watch this receiving cluster be under some extreme duress, you know, doing 20,000, 30,000 inserts a second, which is higher than we'd seen before, and was pretty high for 0.8 days. So we ended up going to 08. We ended up going to a 24 gigabyte heap, which is not recommended anymore. I used to recommend it about a year ago, but what happens is if you don't have a big enough cluster, you're going to have a lot of frustration from your engineers with dealing with just really slow fetches, reads and writes, because the JVM is just sitting there doing GCs, right? You're gonna have 100 milliseconds, sometimes 500s, maybe sometimes 1,000 milliseconds of GC time when you have that big of a heap, just because it's got to scan all that memory. We moved to the latest Java 1.6, moved to the newer kernel because we were on Ubuntu, and the kernels that ship with Ubuntu just aren't as fast as what you can build. 2636 had pretty good XFS, some improvements in XFS, which we were using at the time. And then we moved to MD RAID 5, because we used to be on RAID 0, but what we found was we needed to keep most of the space available, but when disk drives failed, sure, you can just go rebuild the node if it's RAID 0, but the rebuilds would take 2-3 days, and we just couldn't afford to have that much risk exposure, so we chose to go with RAID 5 at the time. And then the biggest thing, the most important thing that I really want everybody to remember is turn swap off on your Cassandra boxes. If you don't have another reason, like you're running other applications that require it, turn it right off. Swap off -A is your friend. You'll have more consistent performance. You won't have as many WTF moments where you're just looking at and you just have these latency spikes and like, what the hell is going on? And nothing's wrong with the system. And when I log into a system, if I see swap going at all, it's the first thing I do, always. If you can't disable swap, I've talked to a few people that say, well, we have applications that really require swap. They, you know, sometimes they'll just run a little over and we just don't want them to crash, so we want some swap available. At least set VM swappiness to 1. So this is talk to your sysadmins, but it's an sesyscontrol.conf. I'll talk about it more in a little bit. But what this does is the Linux VFS cache is really, really greedy. And what it'll do is if you've been using Linux for a long time, you remember the days when locate would run, and you'd come to your box a couple hours later, and none of your shit would work because it had been all swapped out to your disk, and you got to wait an hour for everything to come back. Sometimes you just turn the power off, turn it back on, because it's faster, right? Or you want to log into a system, you think maybe it's swapping, but you can't get in because SSH has been swapped out. All these problems just go away. So what Linux does that causes this to happen is when you do a bunch of I/O, Linux will actually be trying to optimize that for you, and it'll go and steal as much memory from this free memory from the system as it can to make space for VFS cache, which is great, except that now it's swapped out your SSHD, it's starting to try to swap out your JVM, and that's just bad news. Inconsistent performance, really slow, and sometimes the box will just become unresponsive and never come back. If you set VM swappiness to 1, it tells the kernel, it says, I never want that stupid behavior. You take the memory that's free, use that, but never swap out my applications unless you're under extreme duress. More on that in a little bit. So this year, toward the end of last year and beginning of this year, we did this migration again. So I'd gone off to another team. We had some other people kind of take it on as like an extra duty to manage the Cassandra clusters. They forgot about it again. Repairs didn't get run. We had to move to this new hardware because the old hardware was going off lease, stuff like that. And so we just said, screw it, we're just going to do the same process again, revived it, did the GlusterFS P2P, but the big difference here is instead of using our production MapReduce cluster, we just fired up DSE on the new nodes, used DSE MapReduce, which allowed us to basically take all that workload off of our production Hadoop cluster, run it on this new greenfield cluster, and avoid all the issues with like our overloaded MapReduce cluster. This process works really well, and you end up with a nice cleanly distributed. You don't have to worry about like snitch problems or replication problems. It all just works. So we made a few more changes. We did that. Again, this new cluster is different to hardware, different layout, and it's time to tune again. So we're on DSE. We finally switched to packages. We used to deploy with Capistrano, which is a nightmare. We left the heap the same because we still had these massive Bloom filters in memory. I'll talk more about tuning your Bloom filters in a little bit. And we stuck with the same distro on Ubuntu Lucid, which I definitely don't recommend. The whole job ran a lot faster this time. So instead of running on an 80-node Hadoop cluster, which is one of our production clusters, writing into this 36-node cluster, we actually ran the whole thing on there, so it's doubling up its workload, but it still ran faster because of things like DSE CFS is a lot lower latency than HDFS is by default. So it's really nice in that way. When you go and you upload a file to it, it just goes bam, and it's in there because it's built on top of Cassandra instead of this HDFS architecture that's loaded with latency and connections going all over the place. So the mistakes we made, we moved back to RAID 0 because we had problems with disks filling up past the 50% mark again, size tiered compaction bit us again. I would never do that again, because as soon as we did, a couple days later, a couple disks fail on the cluster. Fortunately, they were spaced out in the ring. Those nodes went down, and we had to go and deal with Dell, and our data center's remote. We had to go and do all that stuff, which is why a lot of people love EC2. But the nice thing is if you're on RAID 5 or RAID 6, you just don't have to, you can wait a couple days to deal with it, and that's just really nice. So from this point forward, we're pretty much sticking with some kind of RAID underneath Cassandra. And that's not generally recommended, but it just makes my life a lot easier when you're on hardware. And then we're still being on Ubuntu Lucid, so more recent versions of, I think, also the Apache Cassandra packages and the DSE packages are built on Debian 6. And then basically all the native bits that are built won't actually run on Ubuntu Lucid. They don't match up with the libc. Excuse me. We also took this opportunity to make a few changes to our schema. So when you're doing performance tuning, one of the most important things, probably the most important factor in performance is your data model. In any database, I don't care if it's MySQL, if it's BerkeleyDB, or if it's Cassandra, if you get your data model right, you got a lot of overhead to come up with really good performance. These aren't necessarily data model, but I just want to make sure I mention that. Compaction strategy, we moved to leveled compaction, If you love your ops people, I highly recommend sticking with leveled compaction, even if size tiered's a little bit faster. Leveled compaction is a lot friendlier to your operations people because you don't have that 50% threshold on disk where your size tiered disk usage, once it crosses 50% or 2 times your largest SS table or your largest column family, then basically you're stuck. You got to put more disk in the node or do these kinds of crazy migrations that we've done in the past. So if you're on leveled compaction, you only need enough free to compact 2 SS tables together. So in my systems, I need about 1 gigabyte free. So that was a big change. Bloom filters, so this is changing a lot, especially with LCS in 1.2 and onwards. But prior to that, we found that we ended up running 24 gig heaps because we had these column families where we'd have rows with 15 million columns in them. And those would just use up a ton of space for the Bloom filters. And I was talking to Ben Coverson one day. He's like, yeah, you need to adjust your Bloom filter. And we did, and we actually can drop back down to 8 gig heaps. So GC gets smoother. The whole system just starts running a lot more consistency once you have the smaller heap size. So that's something to look at. That's what I use 0.1. That's not a great value. It's just kind of we just said we didn't have time to really sit and play around with different values, so we just picked one that was basically effectively disabling the Bloom filters, see what happens. We started cramming all that data in, and our false positive rate's still really low. So, and when you're tuning this, you really want to look at, if you look at node tool CF stats, you're going to see in there the Bloom filter false positive rate. That's what you want to look at to tell if you've got the right value. The default is 0.007. I moved up to 0.1. And I still have just a few a day, false positives, which is fine by me because I'm not I/O bound. The other big one is SS table size in megabytes. So this is on a per column family value, if I remember correctly. And what we found is the default of 5 megabytes. So if you have really deep Cassandra nodes, so the recommendation until I don't know what it is right now, but it used to always be on IRC, is like don't go over 200 gigs per node. Maybe on SSD it's a little different, but we're on spinning Rust. So what we found is with the 5 megabyte, we'd have 500 gigs on a node. And that's a whole hell of a lot of SS tables on disk. And when Cassandra starts up, it literally opens every single one of those files and M-maps it. So we used a ton of file descriptors. We ran into limits with M-maps, the Linux setting for max M-maps. And, okay. Where is that? Right. So the JVM and the kernel were spending an awful lot of time just managing all these file descriptors, these huge lists of files that were open. We saw like really high system load. We saw just a ton of CPU usage on a load that really should just be very low CPU and very high I/O. We turned on snappy compression, not terribly impressed. And then we turned compaction throttling right off. I've been told by the DataStax guys this isn't really necessary anymore. The version that we were on, we were doing the migration, had some bugs in that. But what we found is a lot of people are still, I see it on IRC, are running into problems where compactions get behind. I think I might have an example of that later. I have an example of that later, of how to look for it. But what happens is if your compactions get behind, then you kind of get into this loop where you're inserting data. Most of us that are using Cassandra have a pretty constant insertion rate, right? It's not a wave like this. You just have this like 50,000 a second, 24/7, wham, into the database, right? So compaction would get behind for us when we were doing these really high insert rates, and then the next one would come along, and the next one would come along, and they just stack up forever until it was impossible to get out of that mess. We turned the limit all the way up. I said, this disk array should be able to do about 500 megabytes a second. I turned it all the way up to 1,000 megabytes a second, and it still couldn't keep up. Turn it off, it does just fine, right? So if you have Linux tuned just the right way, doing all that extra I/O isn't that big a deal. Most of it's actually happening in memory. There are a couple of settings you can play with to make that even more the case. I'm coming to, and this works just fine. So it might be something worth playing with if you're dealing with that issue where you have really high insert rates, your compactions are getting behind on leveled compaction. It might be worth trying this, especially on SSDs. And then now we're actually working on yet another migration, but this one's not because we screwed up this time. It's because we want to move from our old data center cage into a new, bigger one with more racks available and all that stuff. So we're going to a much bigger cluster. with no downtime. I was supposed to take that number off there. And again, we have to do it with no downtime. So I'm going to move off of this because I wasn't supposed to show it. So what we're moving at to is our new pipeline is going to be, all those events I talked about earlier, those analytical events, are going to be flowing into Cassandra in real time as they come in. And then we're going to be running analytical jobs over that data to do successive aggregations directly out of Cassandra. So both read and write workloads are going to be pretty much equal in a few months. Yesterday, Evan Chan talked about Spark. That's what we're building. So I'm building the bottom half of it. He's building the top half. And we're actually looking at doing an AmpLab. AmpLab just released a tool called Tachyon for, basically it's a front end for HDFS, because HDFS latency, like I mentioned earlier, is really high. So they wrote a new in-memory HDFS cache that lets you do write-through cache, or write-back caching with memory, and it's all in memory. So we're actually looking at writing a Cassandra backend for that so that we don't have to run HDFS in parallel with our Cassandra clusters. So this is the next generation. So a lot of stuff that should be familiar to everybody in the big data community. If you're new to this stuff, I'll quickly cover it. Kafka is a really cool tool. It's, if you're using Storm or Cassandra, basically any of these big data stacks where you want to do real-time streaming inserts, Kafka is a really nice tool from LinkedIn, open source, that basically is a message queue for really high volume messaging. So basically all those logs get written real time as the requests come in into a Kafka queue, and then we have an ingester that pulls off of those Kafka queues and writes into Cassandra. And what that lets us do is if we want to bounce that ingester or have it down for 10 minutes, Kafka will eat up all the writes. And that's generally what you like message queues for. So that's the overview of the architecture. Spark does all of our reads. We may add Tachyon in later. The ingest code is basically custom Scala stuff that we wrote. And that takes the data out of Kafka, does a very minimal amount of normalization, and then writes into Cassandra. So this is my intro into the next section. So I wanted to say something about practical engineering, and this video kind of says it for me, so it's just a few seconds.
Hey, look, buddy. I'm an engineer. That means I solve problems. Not problems like what is beauty, because that would fall within the purview of Gary and others of philosophy. I solve practical problems.
That's the business a lot of us are actually in, right? We're not building, a lot of us aren't going out and discovering new algorithms or building new hot snot like computer systems. We're taking a bunch of components like Cassandra and Kafka and Scala and bringing them together to build an aggregate service that's unique, but from common parts off the shelf. So it's a more practical than pure computer science. And so when we're talking about tuning, there's kind of a philosophy that I have that I've really worked hard to try to be able to share with people. And the main point being is there's a lot more to tuning than just raw performance, right? So the number one is security. It's always security. Your number one on any kind of design decision should always be security. Even if you're turning it off, which a lot of us do with Cassandra, you turn off authentication, you don't bother to do crypto because it's a pain in the ass. You still need to think about it, and it needs to be a conscious decision. Then after that, your cost of goods sold. Like, sure, it would be great if I could have a 1,000-node Cassandra cluster in EC2 on SSD instances. I'd never have to touch a damn thing, right? But my business I'd be spending, $50,000 a month on that cluster or whatever it costs. So you need to think about that. And your tuning parameters, how much memory you choose, how much disk you choose, which kind of disk, that all comes down to how much of the business's money am I spending on this cluster. How much are your ops guys going to hate you or hate themselves? You need to think about that. So when you're picking Cassandra, it's a great database for your ops people, right? A node can fail in the middle of the night, they look at their phone, and they go back to sleep. That's what I do. That's what a good ops person does with a distributed database. But for the engineers in the room, when you're designing your schemas, it might be tempting to mess around with your replication factor and say, maybe 3 is too many. I don't want to store the data that many times. They're running RAID under it. Why was it a big deal? Well, it's a big deal because if your replication factor is 2, that means your sysadmin has to get up in the middle of the night and fix that node, because if the other one failed, if the next node in the replica If the node's replica fails at the same time, now you got an emergency on your hands, right? So just keep that in mind as you're designing schemas, as you're messing with all these settings, is think about what happens in the middle of the night when stuff fails, because it always does. It never fails during the day. It always fails during your kid's baseball game or in the middle of the night when you're just having the best dream of your life. You've all woken up in the middle of the night because something like that, right? So, and then, physical capacity, do I have rack space? Can I get the hardware, so on. Reliability and resilience, I recommend everybody look up John Allspaw's, has a nice blog post and a few talks about resilience and just in general the philosophy of it. I'm not going to go into that, but going back to the replication and stuff, think about reliability and resilience. And then there's compromise, which is probably the one that is the most frustrating to deal with. So you have different business use cases, you have a whole bunch of different engineers that have different opinions on how to build schemas and build databases and which one they should choose. Should we use React? Should we use Cassandra? Should we write our own or have this like mess of level DBs all over 100 boxes? You got to make compromises, and your tuning tuning your system needs to take all those compromises into account. So I think I hopefully got the point across that it's not just the maximum performance that you're looking for. You're looking for the best that you can do. Not the lowest common denominator, but something a lot like it. Hopefully not as depressing. So I mentioned earlier a little bit about the science of tuning. I won't spend a lot of time on this and bore you guys with my philosophy, but the video, the reason why I brought that up is because I'm not a scientist about it. It would be really great if I could spend a month in the lab with Cassandra, playing with all kinds of different hardware and memory and get it just running just super awesome before I show it to anybody. That would be awesome, right? I've done it before, other jobs, and it's fun, but the reality is production comes first, and you got to get the code shipped. So how do you tune a system to the best of your ability without actually going and off and having a lab? So what I'm trying to bring up this term, this heuristic. Like, you got to use heuristics. You got to use your gut. You got to use your education to make decisions. When I'm choosing hardware, I know that quad channel DDR3 is going to do a lot more bandwidth than dual channel, and if I imbalance the banks, then I don't have to test that. Like, it's just that's how the hardware is. So you can make that decision without actually testing it, is what I'm kind of getting at. And your brain is really good at this kind of stuff, right? This is what we do better than computers, and for now anyway. So you should learn to use that ability. If there's a really good book by Malcolm Gladwell called Blink, that's all about this kind of stuff and how gut reactions will often beat clinical studies and scientific, very, very measured control group and being very careful studies. And they did studies with doctors and things where they found that you could go through this procedure that was designed in a lab for treating heart patients, but they found that if they just had the doctor make a quick snap decision out of his gut, that outcomes were better. And there are a lot of factors to that, but I recommend the book highly. And then back to the practical approach is just concentrate on bottlenecks. Look at your cluster in production, and look at what's slowing you down. Are you doing a lot of I/O? Does it look like your memory bus might be oversaturated? If you see one process, if you open up top and you hit H and you can see all the threads, and there's one thread on top doing 100% CPU and all the rest of them are idle, you probably have GC problems. And I just wanted to mention this one real quick. This is kind of getting popular in the ops side of the world, is the OODA loop. This comes out of the military. There's a really good Wikipedia article on it if you want to Google it. But it says, this is my slight variation when I'm tuning is, you observe production systems under load, under your load, because it's the only thing that actually matters. Nobody gives a crap if you can make Cassandra super fast in the lab, and then you put it in production, and your production load crushes it, right? So tune with your load. If you can replicate it in the lab, great. But a lot of us can't. We don't have the resources. We don't have the money. We don't have the time. So you have to observe your production clusters in production and make changes, safe changes that you're confident about. Maybe you test those on a small setup in EC2 for a couple days, shut it all down, and then try it if you're not confident. If you are confident or you're crazy like I am, You just make the change in production on 1 or 2 nodes and then roll through, and you can make these changes with confidence because you just get good at knowing what the health of your cluster is. I won't spend any more time on that. So that's basically what I'm coming to is, I love testing shiny things. I love playing with these settings. I love getting an extra 1% out of my cluster. And I know I'm kind of on the outside with that, but Linux kernel has come a long ways in performance in the last few years. If you're on CentOS 6, your kernel is missing probably 20% performance overhead on a lot of things. The memory subsystem has gotten a lot better. The I/O subsystem has gotten a lot faster, a lot more parallel. Most of the file systems have gotten better. I've run into weird bugs like XFS has had this bug a while back with, if you set Alex size to anything, so you could set XFS up so that when Cassandra goes to do a write on an SS table, right, it opens up a file and it goes to write the first byte. Under the covers, XFS would actually go, if you set this value to like Alex size equals 64 megs, it's a really cool optimization, right? Because it goes and allocates the whole 64 meg chunk under the covers right as soon as it gets the first byte written to the file system. So you don't, all the successive streaming right out of Cassandra, you don't have the overhead of going and finding an open block on the disk. So it can just stream it all out as fast as possible. Except there was a bug, and that if you only wrote out like 5 megabytes, that 64 meg chunk, it would still leave the 64 megs allocated on the file system, and your disk could fill up like in a couple days, especially on LCS. I like playing with different Linux distributions. I don't typically do that in production, but it's something that comes into play. A lot of people just pick CentOS because that's what their organization uses, or they pick Ubuntu because it's cool and popular with developers. But there are things you can do with those distributions by changing out some of the components, looking at what JVM am I shipping. Obviously, most of us are shipping our own JVMs for that. The kernel that ships with it, which libc is it, and how is it compiled, and how much performance can I extract out of that, because the JVM depends on it very tightly. Playing with different file systems. We're running ZFS on Linux in production now, and it's awesome. You get most of the advantages of ZFS, and it's in kernel, and it's fast as hell. BTRFS is really interesting because it's in the Linux kernel. It ships with most of the distributions now. It has some of the features of ZFS. It doesn't have any of the performance features, but it does have LZO compression. It has support for SSDs with trim commands. It does its own version of RAID 0 that's built into the file system so that the file system is aware of where the blocks are distributed and can do optimizations that you can't do with these successive layers of LVM and MD RAID, and the disk device is abstracted so far away that the file system has no freaking idea what's going on. And then different JVMs. Does OpenJDK viable yet? It's not, but it's worth trying every few months just to see because they are advancing pretty quickly. And then I test all these things in production. None of the things I'm running in production today started out in the lab. All of them started on a production cluster. And here's how I do it. So Cassandra actually is perfect for this kind of crazy stuff, right? So you have a new kernel you want to try. Say 3.11 comes out, and it's got some really cool optimizations for memory bandwidth. What you do is you just take advantage of the ring. So you have your ZFS file system between two ext4, your well-known, stable, well-working nodes. And you know that you have replicas elsewhere in the ring, so you don't have to worry. If that node completely crashes and corrupts your data, which hasn't happened to me yet, but it could, then I have a backup. I can always rebuild that node back to baseline. So this is one of those things that comes up with these new distributed systems where your data is highly replicated. You can make these changes in production, I think, without having to resort to building a lab, because it's never going to be to the scale. I mean, some of you may have the resources available to do that, but most of us don't. So this is worth thinking about, talking to your peers about, because they're not going to be comfortable with it. Most people aren't. But it does give you a lot of ability to move forward quicker. A little more. So now we're moving to the tools, which is how you stop that. I was going to do one of these charts, but Brendan Gregg did one at scale this year. You can find this online if you search for it. Just search Brendan Gregg tool chart or scale 11x, and you'll find it. The link will be in the slides when they post them. But this chart has every tool that you really need to do this job. It has a few on there that aren't really common. dtrace on Linux isn't really widely deployed yet. But things, vmstat, pidstat, mpstat, especially dstat, for one of my personal favorites. Having this around just helps you when you're looking, when you know which part of the subsystem you want to look at. This chart has most of what you need. I'm not going to go into all of it.
The answer is what?
So this is dstat. I leave this thing running on every one of my systems. So when I fire up my workstation and I start screen, you ever notice that your lights dim every once in a while? That's when I start up my screen session. Because it logs into all of my systems automatically, and it starts this dstat command, dstat minus lrvn10. Now dstat has a bajillion options to it. It can pick up system stats from just about anything, and it's written in Python. Writing plugins is something like 60 lines of code. And then what it does, it just sits there, and the 10 means that every one of these lines changes every 10 seconds. They update every second regardless of what you say on the command line. And so what you can see here is, when I'm looking at this on my production systems, what I see in this middle part where you see kind of a lot of yellow over there on the right, that's where our MapReduce load is running and writing into the cluster. So I can see about how long that's taking. I can see that right from the system. I don't have to look at anything else. I can see it all right here. I can see that, my CPU, the green line that's idle CPU there, that never really gets too crazy. There's a fair amount of I/O wait, but it's reading and writing at a fairly high rate. I'm pretty comfortable with these stats. But I can see how much VFS cache I'm using. I can see this all at a glance. So I can flip through the cluster, Control-A-N, flip through 36 nodes, and just quickly look through and see. dstat, tuning on a single system, absolutely the best Linux performance tool there is, in my opinion. So this is my tool I wrote. It's on GitHub under github.com/Tobert, Perl SSH tools, terrible name for it. But this, of all the tools in that repo, this is the one that I use the most often. And what this is I started from a tool Colin Razor wrote long time ago in Perl that basically would read the procnet dev file on Linux, which actually has all this really detailed information about what your network devices are doing. Well, I wanted to add a disk stats, and I wanted the load average. And then I wanted to be able to do it at a whole cluster at a time. So all this does is it opens persistent SSH connections to every node of my cluster based on a cluster list and starts reading those files every 2 seconds. And this thing updates every 2 seconds. So I can see in real time how much network traffic I'm doing, how many disk IOPS, and what the load average is, which gives me a rough idea of how busy the CPUs are. And then I can see in aggregate what my clusters are doing. So I've had this thing up to 300,000 megabit on our new stuff, just display, and I can see what nodes are busy, and I see that something like this line down here, this green line, is showing me that I got a node that's not doing anything. What the hell is going on? I should probably go look at that. Is Cassandra down? Is the MapReduce stuff failing? There's something wrong. So I use this for every kind of cluster we have. Hadoop, Cassandra, Riak, anything I'm working on that has more than one node, this is how I watch them. And I'll leave this running 24/7. This is the old standby. If you're having I/O issues where you have a RAID array, especially software RAID, and it's just slower than it should be, right? Especially RAID 0, RAID 5, not so much with RAID 10, but it can still help there. Usually what's going on is you have one bad drive in the RAID array, right? If you have hardware RAID, this stuff is hard to see, and generally it'll fail it out after a while for you automatically, and it's built into that black box software. But if you're running MD RAID, what this will show you is you want to look at the only important thing. Use dstat for all these other numbers, but for the A weight, the RA weight, and WA weight, what you're looking for is no particular value. What you're looking for is a different value. So if you have 6 disks in a RAID array, and this thing is ticking along every second or 2 seconds, and you see that the weight is higher on one drive than all the others, and sometimes it'll even be an order of magnitude, it's probably a bad drive, and you should either wipe it and reformat it and see if it comes back to normal, or you should just throw the damn thing away and get a new one. HTOP, so if you're using top, you should probably install HTOP. It's a better top than the one that comes with Linux. It shows you all the threads by default, so you can see GC problems right away, because there'll be that one thread on top that's doing 100% CPU while all the other ones are idle. That's almost always GC issues. And that goes for most Java apps. And I really like the CPU bars. This thing is infinitely configurable. You can put all kinds of crap on there. I work on too many systems, so I just use the defaults. JConsole, or if you're using Oracle JDK, you can use Visual VM. It's a lot of the same stuff. Visual VM is just a much nicer version of JConsole, but JConsole is in every JDK, including OpenJDK. And I took a screenshot of this screen specifically because this system has its XMN size is way too small. So you see the sawtooth going on? That's because what's happening is filling up the Eden space, and then GC fires, and then it goes all the way back down. And as soon as you hit that GC, that's where you get screwed on latency. Now it's pretty fast, but like if I want to see this get a lot smoother, so that's what we're working on. We're tuning a lot of these clusters. Op Center is pretty handy. This is that big cluster again. I thought that was pretty fun to show. I love the ring view, because these balls in Op Center will get bigger and smaller depending on how much data is on your node, so it'll show you imbalances in your cluster really quickly. It's nice and visual, and it looks really cool on a dashboard at the office too. Just tell people you wrote it, and they'll think you're a rock star. Everybody knows about node tool ring. It's the first thing you check if you're working on a Cassandra cluster. And I just kind of highlighted an interesting value. We built this cluster just really quickly to do some quick performance testing. And there's one node that owns 11.6% of the data. That's going to be a hotspot, guaranteed. Node tool CF stats. I don't get into these commands too much because I do most of my tuning from the system side, looking upwards. And I don't really look at the database that often unless there's something specific that I'm looking for. In node tool CF stats, what I'm looking for is if that SS table count is really high, then I might look at tuning the SS table size in megabytes to get that lower. And then the Bloom filter false positive ratio that I mentioned earlier, that you'll want to tune if you're using a lot of heap. Your mem tables are flushing way too often. You can either increase the heap or you can tune that downward, and there's another one, there's an index interval that you can tune down to save a lot of memory. DataStax guys have some good docs on these settings. I won't go too far into it. Proxy histograms, I don't know what the hell this says. It looks really cool though when on a busy cluster. Compaction stats is where you look for if your compaction, you think your compaction is getting behind. This will show you that really quickly. This is from our metric system, the one doing 50K a second. These were run about 2 minutes apart. So I can see that it's making progress on compactions, but it's a little bit behind. It's not where I like it. I'll probably tune the IO subsystem to get that, or grow the cluster to bring that down. So stress testing tools, I'm almost done, so there's time for questions. Cassandra Stress obviously ships with Cassandra. It's got 1 million parameters. You can fire that thing up. You can tune it. You can get that thing to do workloads that are very similar to yours if you spend enough time with it. And so I recommend learning how to use Cassandra Stress. Really spend some time with it. We run it in production against production clusters sometimes. It's dangerous, so we'll do it in times when it's all hands on deck. So if something goes wrong, we can fix it. But it's a good tool to get used to so that you can basically, when you bring up a new cluster, just burn it in, make sure everything is functioning before you put load on it. It creates its own key space. It's really easy to clean up afterwards. I haven't been able to spend much time with it, but Yahoo has a benchmark called YCSB. It's on GitHub. It looks pretty neat. It's a multi-NoSQL database benchmark. We'll probably publish the numbers from our clusters in a few weeks. Like I said, I like to use production load to stress test stuff. Wherever possible. If you're running DSE, Terrasort is kind of the standard Hadoop benchmark. That's a good one to run when you're burning in new Hadoop or DSE clusters. And then my personal favorite is homegrown stress testing tools. So they're not that hard to write. A lot of times I've noticed with benchmarking tools, maybe you have too, a lot of the benchmarking tools, it takes you months to learn the darn things. And by the time you do, it's very specialized information. It's not useful for anything else. Or you could just write the code to generate the load that you want. And that might take you half a day, and then you have absolute control over what it does. And measuring latency and things like that just isn't that hard. So it's something to think about and make a case for yourself if you're confident in doing that. I will talk to people about this later. So syscontrol.conf, the slides come out. This is my default settings. I put this on every machine before I test anything because the Linux defaults are broken. Just keep that in mind. The defaults that Linux ships with are for Linus Torvalds' workstation under his desk at his house. And he's not shy about that. So you need to tune stuff. Dirty ratio, dirty background ratio are the ones you want to read the most about. The kernel PID max one, that's just what I do for fun. It actually doesn't fix anything. It just means that now your PIDs can go up to 1 million. So if your processor are flying by really quickly, they don't roll over as often, so you get a nicer PS listing. A lot of people still put tuning information RC local. There are a few things that don't really have a good place elsewhere. The bottom one is the most important one. Well, the bottom two. So the scheduler one, where it says CFQ. CFQ is the default on most Linux distributions today. You should if you're not running any other applications on your cluster, then you should probably look at Deadline. Deadline is almost always better for latency than CFQ is, especially on drives other than SATA drives. So if you have fast SAS drives or anything, switch to Deadline, you'll get better I/O immediately. And then if you're running RAID 5, the stripe cache size, I'm not going to go into that, but by bumping that to 16K from the default of 128, we picked up about 100 megabytes a second on RAID 5. JVM args, real quick. Don't mess with the defaults if you don't know what you're doing with the JVM, but the big one that you want to tune is the XMN, the new size. DataStax recommends 100 megabytes per actual physical core. That's actually a really good recommendation. And the other one I've been experimenting with is the JVM support for NUMA. So Apache Cassandra scripts ship with NUMA control interleave built in. So if it sees the NUMA control tool installed on your system, it'll use it to basically make sure that memory allocations are balanced across NUMA nodes. If DSE doesn't do that, or at least it didn't last time I looked, but this XX minus XX plus use NUMA means that the JVM will become NUMA aware and will automatically balance its allocations and talk to the Linux kernel and tell it where it wants the memory allocated. And I believe that the GC is also aware of NUMA at that point too. I am running out of time, but so cgroups, I'm going to say that it's something that if you're a systems administrator, you need to learn about. Absolutely, you want this on every system that you manage because it gives you much finer grained control over resources on Linux than you've ever had before. So that stuff I talked about earlier with Linux systems becoming unresponsive or just, you have weird scheduling problems, right? The Linux scheduler is notoriously just a pain in the ass. So by turning on cgroups, you just give it a lot more information. You can say, these threads go together, or these processes go together, and it's on a per task basis, which means threads and processes. And it's all just a file system interface in the kernel. It's really easy to work with shell scripts and things like that. I'll probably be blogging about this in a couple weeks about how to use it without all the LXC madness. There's more. This is kind of how I do the default setup of cgroups. This will also be in the slides. I just put this in. If you're running Apache Cassandra, there'll be on Debian, there's the etc default Cassandra file, or DSE, it'll be etc default DSE, or for Red Hat, it'll be like etc sysconfig, something like that. And it's just a shell blob, so you can actually put shell commands in there. So what I'll do, and it's running as root, so I'll actually put the cgroup setup in that file, which is kind of a dirty hack, but all the child processes inherit the cgroup. So you can actually do this and put Cassandra in one cgroup, and I'll actually run 2 clusters on the same hardware and just separate them with cgroup resources, and they can coexist just fine. No virtualization necessary. And I'll take a couple more minutes. So we're running BTRFS in production. We're almost done. We're running RAID 0, BTRFS, and EC2 on ephemeral drives. It's really nice. We turn on LZO compression, which gives you a lot more compression than Snappy will ever give you. I believe the LZ4 stuff will get pretty close. It's within striking distance, so if you're on Cassandra 1.2, you might want to look at that. But BTRFS is really interesting. It's not considered stable in the distro community yet, but there are, like Fedora starting to ship it and allows you to install root file systems with it. Ubuntu's looking at it. And I've been running it for about 1.5 years now and never had a crash on it. They say that the big corner case is around filling your disk and stuff, but I just tend to tune my systems to stay the hell away from those kinds of corner cases in the first place. And then finally, this is my last kind of show and tell item, is ZFS on Linux. So ZFSonlinux.org. These guys, Los Alamos Labs took the ZFS code from OpenSolaris, and because Lustre had actually switched entirely over to ZFS, they ported it to Linux so that they could continue to use Linux. And then they successfully built back up all the layers of ZFS on Linux so it all works fine with the Linux kernel. It's not the fuse stuff, it's actually quite fast. It's not 100% of what it is on Solaris yet, but it's pretty damn good, and it gives you all the flexibility to do crazy things like, I didn't put it on here, but there's a setting where you can do ZFS set sync equal disabled, which is a really fun performance trick, because it basically means ignore fsync like it never happened. Tell the app it did though. So Cassandra will go and say like, okay, I wrote this data to disk, now fsync, make sure it's written to disk and don't return to me until it is. ZFS will go, okay, it's written to disk, and then it'll write it to disk later, and it'll lie. Now I'm not recommending that you do that, but occasionally it is really fun. And then you also have compression. There's snapshots built in the file system. BTRFS has that as well, which can be handy even though Cassandra has snapshots. And so finally, tuning is multidimensional, like I talked about. There's all kinds of different parameters that come in, and performance is by far not the most important one. Stability, security, all of these things all are big factors. Do you have the money for it? The boss saying no. They like saying that. Production load is all that matters in my mind. Like, I don't really give a crap how fast something is in the lab. When I put my load on it, will it survive? Will it wake me up in the middle of the night? Those are the kinds of things that you should be thinking about, not how fast can it be. You just need to make it fast enough. And Cassandra generally gives you that by default. And then lean on Cassandra. Like, it's a really great database. It's super stable, and it's distributed, so you can mess with a single node. You can kill -9 Cassandra and just see what happens. And I do this in production sometimes, just to keep Phil on his toes. You should run experiments, and just if you want to be scientific, do it outside of the system. Keep a spreadsheet and do A/B testing. And then no one metric tells you the whole story. CPU load, I/O load, all of these things have interplays, and you can tune for CPU load, and all of a sudden your I/O subsystem is screwed, and you really need to balance all these different things to really have a really well-functioning system. And with that, I'm done. It's my contact information. I do tweet a lot about Cassandra, and then on my GitHub there are I have a lot of gists related to Cassandra, and then the Perl SSH tools, and then you can email me if you have any questions. Thank you.
Does anybody have any questions to ask? No questions. Seriously.
Like, when were you certified?
Okay, great presentation.